This is a sample of the highest rock in the world. One down, two to go. Kenton descends further to collect the next sample. Just below the summit, the rock changes. Climbers call it the yellow band due to its distinctive color. The rock is dramatically different from the summit. Much harder and yellow in color. This is a layer of marble.
All right, there we go. This is off the yellow band. All right, so that's that. That's the yellow band. We've collected samples from here. It's not been very easy. We're getting out of here. It's beginning to snow.
But he has one more to go. Kenton starts the long descent to where he'll get the next piece of evidence. He enters into the Western Cwm, a huge U-shaped valley which has been carved by the Khumbu Glacier, a frozen river of ice that has relentlessly pushed downward over the past million years. Rock and debris in the glacier have ground away at the rock underneath, revealing the base of Everest. Kenton needs to take his final sample from this area of distinctive white rock, granite.
So here we are in the Western Cwm on Everest, about 6,400 meters. I'm actually stood underneath one of the easier outcrops to get to. This is a big sort of granite cliff above me.
This white rock is full of crystals. It's extremely hard and different again from the summit limestone and the marble.
Yeah, we've got quite a nice sample of the granite there.
With the three precious samples safely packed away, Kenton takes them to the University of Oxford. Here they will be analyzed by the world's leading authority on Everest, Mike Searle.
So Mike, this is your summit rock. Now, that is from the top of the world.
Well, this sample, Kenton, is probably one of the most important samples of the whole expedition, so it's literally worth its weight in gold geologically. This came from the summit of Everest right there. The next rock down that you collected was from the yellow band. And even further down is another rock, a granite.
Almost a complete picture of Everest.
That's right, yes.
Fantastic.
Yeah.
These three rocks are the major components which make up Everest.
All that effort to get up to the summit was, I can tell you, was absolutely worth it to get this sample.
Good. I hope so.
So the next step is we want to find out what's in it.
The summit rock is cut into a thin section. So thin, light can pass through it.
Okay, let's have a look at this slide of a limestone that's from the summit of Everest.
The highest rock sample in the world reveals its secret.
Oh, that was interesting. What's that? We've got a section here through a crinoid stem. A crinoid is a sea lily.
From fossil records, the section can be dated. It is over 400 million years old. The sea lily is evidence that the summit rock of Everest was formed in an ancient marine environment.
So from seeing this evidence, we can categorically say that this rock would have started life at the bottom of the sea floor. And then I've collected it from the very, very top of the world, from the summit of Everest itself. That's just amazing.
But a mystery is revealed. How had rock with marine fossils in it ended up on the top of Everest? The mission to collect rock samples from Everest has uncovered two clues as to how it formed. Samples show that the mountain is made from three distinctive types of rock. Rock from the summit of Everest contains marine fossils, proving it started life on the bottom of the sea. To figure out how seafloor came to be on top of the highest mountain in the world, geologists need to find evidence that is millions of years old, going back way before the Himalayas were even formed. 400 million years ago, no trace of the Himalayas existed. The sea lily, now fossilized on the summit of Everest, is proof that there was once water where now this great mountain stands. But to figure out whether this was just a shallow inland sea or a great ocean, geologist Mike Searle travels to the Himalayas. He begins the investigation at the Garkola River. It flows down from the high Himalayas and carries with it an intriguing clue.
The rock I've got in my hand at the moment may look a bit boring and insignificant. It's just a pebble taken from the river, but it's actually a key clue as to the formation of the Himalayas and the evolution of the rocks. It's almost by magic, but when you smash a rock like this open, what it reveals inside is an absolutely beautiful fossil. And this fossil is what we call an ammonite.
This ancient creature is part of the squid family. It's proof of a complex ecosystem found in a deep ocean.
Giant squids swimming around in the seas that once lay between India and Asia, and this is some of the key evidence that we've got, that there was a major ocean between the continents.
But to find marine fossils in the high Himalayas and on the summit of Everest, some immense geological force must have pushed the ocean floor upwards, above the water. Figuring out how this happened has taken geologists over 100 years. The first lead in this investigation came from an unlikely place: Antarctica. In 1910, the renowned Antarctic explorer Robert Scott began his ill-fated expedition to the South Pole. After reaching the pole, Scott and 5 of his team died. When the bodies were discovered, among their equipment were carefully wrapped and labeled fossils. The fossils were part of an ancient plant called Glossopteris, and specimens are preserved at the British Antarctic Survey.
Glossopteris is a type of plant known as seed fern, and from many different lines of evidence, such as roots and leaves and preserved trunks, paleontologists think that Glossopteris is actually a type of tree.
Soon, this humble tree fossil was found across the globe. In India, South America, Africa, Madagascar, and Australia. Geologists now had a puzzle. How had this one species of plant spread between continents, separated by thousands of miles of ocean?
Glossopteris is a very important fossil because it could not have dispersed over vast distances. It couldn't have just been dispersed by the wind or by birds across oceans.
If Glossopteris couldn't cross oceans, then scientists were left with one conclusion. When these trees were alive, 250 million years ago, the continents were all joined together. They were part of a supercontinent geologists call Gondwana land. Glossopteris was able to spread across this ancient landmass. But then, Gondwana was split up by violent tectonic forces, which pushed the continents apart. And 80 million years ago, India broke away from the supercontinent. It traveled north and eventually smashed into Asia. To get the full picture, geologists now knew they must get an exact date for this collision. Once again, they turned to marine fossils.
We know the age of collision of India and Asia from several factors, but the most important one is the age of the youngest marine fossils that are preserved along